A couple of things I just want to point out to you guys. I could ask this in this exam. I could ask, starting with an ester, make the Claisen, and then synthetically apply what you learned in chapter 22. Okay, so you learned about the acetoacetate ester synthesis, the malonic ester synthesis. The only difference is G for the acetoacetate synthesis is a methyl group, so it's a methyl ketone, keto ester, whereas in the malonic ester synthesis, I have a diester. Okay, and notice Dr. Schwann should have talked about how you want to use the same base as your leaving group, right? So the base here is going to abstract this proton that's highly acidic, right? Make this enolate here, and then you've learned about that you can alkylate it, right? And then you also learned that subsequently, if you hydrolyze the ester and make the carboxylic acid, and if you heat it up, you get decarboxylation to lose a molecule CO2 plus the ketone. Okay, so again, I want you guys to remind yourselves that in chapter 23 and chapter 24, we're applying everything that you've learned in the carbonyl chapter. Okay, so this is just an example of that. So now let's talk, this is all review stuff, so let's talk about new chemistry. So what is the Claisen condensation reaction? The Claisen condensation, once again, is an effective method of making beta keto esters. Okay, so one of the things that I often see is that most textbooks always start off with the simplest example. The simplest example of the Claisen condensation is esters of acetic acid. So here I have a CH3CO double bond O. In this example, I have O-ethyl, but this could easily be O-methyl. Okay, so this is ethyl acetate here. If I take ethyl acetate, and what I'm going to do is I'm going to form this species here. Okay, and then subsequently I'm going to add an acid source at the very end, and I'm going to get this beta keto ester. Okay. Now recognize the following. So this molecule here has how many carbons? It has 1, 2, and then it has an ethyl group, right? So it has 4 carbons. Over here, am I getting 8 carbons?
No, only 6.
The reason for that is you're going to eliminate an ethyl group from the leaving group. So the way I want you guys to think about this is highlight not the ester part, but highlight the fact that we're taking whatever's to the right of the carbonyl at the alpha position, right? So in this case, this is 2 carbons, and I'm going to make 4 carbons if I don't include this ethyl group here. So 1, 2, 3, 4. Okay, so it is a dimerization in a different way, but again, it doesn't add up because we have the elimination of this ethyl group. Okay, and so here's just an example of its utility. If I take this molecule here, which is ethyl pentanoate, I generate 77% of this keto ester. Okay, and notice, could I do chemistry with this keto ester? Absolutely. All of you guys should recognize this product has an acidic proton here. So what if I asked you to alkylate it using methyl iodide or benzyl bromide? And then what if I asked you guys to hydrolyze it followed by heat? I expect you guys to basically recognize that it would decarboxylate.
We can also halogenate it, correct?
Yes, you could halogenate it in some positions, yeah. But I would definitely do that specifically after I would decarboxylate. Because again, it would be less, you have multiple enolizable protons here. Okay. So formally what we're doing, this is just a cartoon. And again, I haven't got into the mechanism, which is fairly easy. So formally what you're doing is you're going to lose a molecule of the alcohol. So whatever the leaving group is, in this case it's ethoxide, I'm basically going to have a proton coming off the alpha position and protonating this guy to give you the alcohol. Okay, so in principle it looks like that, not really, okay? But again, it's just a cartoon. So what is going on mechanistically? Well, the first step of the ester, okay? Basically, of the ester is deprotonation to make the enolate of the ester. So I'm going to take ethoxide, which is my base. I'm going to abstract this proton and generate this enolate. Okay? So again, just to re-emphasize what I shared with you guys earlier, can sodium ethoxide attack as a nucleophile to the carbonyl? The answer is yes. But guess what? You get the same product because I have the same leaving group. Right? So, yes, ethoxide can function as a nucleophile, but you get nothing. We really want sodium ethoxide to react as a base to abstract that proton out the alpha position. Okay? Now, one of the things I don't have here is the pKa values. So the pKa value for this guy, please write this down, is 25. The pKa value for ethanol is what? 16. Okay? So think about this first reaction in acid-base chemistry. I have a weak acid going to the stronger acid in ethanol. Okay? Notice that we always talked about the direction. Strong acid, strong base always goes to the weaker acid-base pair. So if my products have the stronger acid and stronger base, notice the equilibrium is shifted not towards products, but towards reactants. Okay, so actually, let me go ahead and do this for you guys on a piece of paper. So I'm going to stop sharing